going on. Right. So you can see that, I mean, just by looking at it, that we're going to have a fair amount of critical values. Right. So, and if anybody's looking for typos, you can see that the font is a little weird. So, take advantage of all that stuff. Right. So find, investigate the critical points of the function f of x y equals cosine x cosine y, cosine x sine y. It's very innocuous looking function. It doesn't look like it would hurt a fly. So let me get it into GeoGebra. Get out of here. So z equals cosine x sine of y. Yeah, you're like, oh, that doesn't look like anything. Oh, well. All right, so it's definitely got that egg crate look to it. At first glance, if you get a little sideways view of it, a little profile view, depending on the angle you take, it definitely looks like a trig function. If you get a different angle, it looks like a sine. Well, this would be a cosine function. If it were in two space, a cosine function that's also a reflection over the x-axis, in this case, the xy plane. But we see some symmetry. It looks like, if I had to take a guess, it looks like all our maximums are going to be at the same height. If I really had to take a guess, I would be thinking 1. And all our minimums would be at -1. It looks like we have some saddle points possibly. Okay, so let's see where those come into play, but I don't know if I can bring it in enough to really accentuate it. But if you kind of look at any one of these, it's like if anybody's, all my analogies when it comes to this involve skiing. If anybody's ever skied moguls, you recognize this pattern. Just imagine it on an incline, and so you have a little piece of it in the valleys where each one of those valleys, and let me just bring it in over here and do it. You have these peaks and valleys where you look at the point, like a point over here, and you say, well, that's a minimum. But what I'm saying is, if you come at it from this direction, you're actually climbing uphill to get to that location, because this is the true minimum. So you're actually climbing uphill to get there and then coming back down. So some of the valleys are actually hilltops, depending on the direction you're coming from. So those instances, those would be saddle points, right? And they're going to come up in the process of finding critical values, where you see that you have those points that are neither minimums nor maximums, because they're both minimums and maximums, if that makes any kind of sense, right? Depending on the direction that you're coming. All right, so that's what we got to investigate. We got to get unique points that represent the minimum, local min, local max, and saddle points, because we know they're there. All right, so we start off, because you're not completing the square for this. We start off by finding the first order partials with respect to x and y. So with respect to x, cosine goes to negative sine. Sine y stays put. First order partial with respect to y. Cosine x stays put. Sine y goes to cosine y. All right, so we have at least that part of it. Now what we can do is set them equal to 0. Now, one thing that didn't come up in the last problem is we set our first order partial equal to 0, but we also set them equal to each other. It's just we got constant values, when we set our first order partials equal to 0 for the last problem, that there was no way we could set them equal to each other, right? The idea is that what we're looking for are the different ways in which our first order partial could be equal to 0. So f of x would be equal to 0. No, I'm sorry, f sub x. So negative sine x sine y can be equal to 0 when sine of x, negative sine of x I'll take, is equal to 0, or sine of y is equal to 0. Right? Either or, right? Because if either of those, because it's a zero product property from algebra 1. If either of those are equal to 0, then the whole first order partial goes to 0. Same idea for the first order partial with respect to y, cosine x cosine y would be equal to 0 when cosine of x is equal to 0 or cosine of y is equal to 0. Right? Now, these two things have to happen concurrently. So all of these are separated by a nice looking logical and symbol. Right? So we're looking at either of these being true, either or, and also either of these being true, either or. All right. So my underlining is making a mess, so I'm just going to. All right. So now we start getting into the trig aspect of it, but unit circle trig is you know, it is what it is, but this is not, this part of the unit circle is not what makes it difficult. Sine is equal to 0 whenever the function is on the x-axis. All right, so we're stuck with an unrestricted domain in the sense that they didn't tell us only go out so far in terms of x and so far in terms of y. All right, so we're working in the realm of negative infinity to infinity. So the domain of the whole thing is x, y, such that x and y each belong to the set of real numbers. Okay. So that sucks, because if they said negative 2 pi to 2 negative pi to 2 pi or negative 2 pi to 2 pi, we would have a finite set of answers, but we have to account for the fact that it's not going to be finite. All right. So x can be equal, and for this piece, could be 0, could be pi, could be 2 pi, could be everything in the opposite direction. So what I would say is, you know, just to start listing a series of values, sequence of values, and then generalize. So x could be equal to 0 plus or minus pi, plus or minus 2 pi, and so on. But you could also write it as x can be equal to 0 plus pi k, where k belongs to the set of set of integers. Real numbers wouldn't make sense there. All right, so that's if you wanted to generalize. Now, 0 plus pi k is really the same as saying just pi k, right? But I'm indicating it as a linear relation where I have a start and then a slope, you know, so it's just something that I prefer to do. So, or y, well, y is same deal, right? So it's still a sine function. So I put the or in between. I mean, you get the idea. I ran out of room, so it is what it is. But then we look at the same thing, but for cosines, same idea for cosines. Cosine can be equal to 0 whenever you're on the y-axis. So that's pi over 2, and 3 pi over 2, 5 pi over 2, and so on. So I'd be looking at x is equal to pi over 2 plus or minus 3 pi over 2 plus or minus 5 pi over 2. And then that would generalize to pi over 2 plus pi k, where k, you use whatever variable you want, but it would belong to the set of integers. All right, pretend that looks good. All right, and so same idea for y, because it's still the cosine function. All right, so these are a couple of ors, each separated by an and, or each set of ors separated by an and. So I'm just gonna put a big old and right in the middle. So this or this set, that's gonna give me my, oh, if only. It's going to give me my set of possible critical values, but you can see it's not as simple as 1, 3. You know, there's a lot more going on here than that. Right? It's a lot more in terms of ingredients. So when I need something, or what I need is something that's going to satisfy both groups, but from within each group, I have choices. All right, so I'm looking at this being like, okay, well, let me take, I guess I'll take an X from the first group and I'll take a Y from the second group. Yeah, that'll get the job done. So let me get an X from the first group. And a Y from the second group. And I'll call this the first group. And this will be my second group. All right, so I'm looking at all my possible X's. Well, I like the sound of 0. So how about that? X equals 0. And for my Y's, well, I can't take a 0. I'll start simple. How about Y equals pi over 2? All right. So I already have a sense going into this problem where the magic is happening. You know, we know that there's going to be a max, there's going to be a min, and there's going to be a critical point. I'm sorry, saddle point. We also have a sense that possibly the max is at 1, the min is at -1. So the saddle point looks like it's sandwiched right in between, maybe 0. So keep that in mind. But we do want to go through the process of investigating all of this. All right. So that process involves the second derivatives test or using some other intuitive approach. All right. One thing I could do is evaluate the original function at these 2 points. So I could find f of x comma y, specifically f of 0 and pi over 2. So that's cosine of 0, sine of pi over 2. So just evaluate the function. Cosine of 0 is equal to 1, sine of pi over 2 is equal to 1. So that gives me an idea that maybe a local extreme value is going to be at, well, 0 and pi over 2. So what I could then do, so I'm going to continue with this investigation with the idea of taking an X from the first group and a Y from the second one, just because I don't know if that's going to be the case for all of the X values from that set. So maybe I'll just grab another one to be sure. Let's say X is equal to pi and Y is equal to, I'm just advancing it by pi radians. So Y would go to 3 pi over 2. All right, so if I evaluate this at these locations, cosine of pi, sine of 3 pi over 2. Cosine of pi is equal to -1. Sine of 3 pi over 2 is -1, so I get a +1 anyway. All right, so far so good. So we're on to something here. It looks like maybe anything that follows this sort of relationship is going to be a relative max. But let me just try one more. All right, because I don't want to be caught out in the rain here. So let's try x equals pi. I'm going to keep that as x equals pi, but this time let me go with y equal to pi over 2. So I advanced the pi, but for pi units from 0 for x, but I kept the original. So going back to this here, I advanced this by pi, but I kept this the way it was. All right, so that would be f of pi comma pi over 2, which would be equal to cosine of pi sine of pi over 2. Cosine of pi is -1. Sine of pi over 2 is +1. That gives me a -1. So it isn't just a simple matter of picking values that are just from this x and just from this y, and you get what you need. There's a certain flavor to it, right? In order for this to play out as a case where you're going to end up with a relative max, the signs need to be the same, right? So I would need any instance. So from the first group, if I want a relative max, so from my first group, if I'm just focusing on the x's, I would need some value that's going to give me the same sign as whatever value I choose for my second group. All right. So if I think about sine of x, so again, the function that I'm working with here is sine of x cosine of y. I'm sorry, set it backwards. Cosine of x sine of y. I need the cosine of x to be, our choices are, so far, it seems like from those two groups, it seems like our only possibilities are +1 and -1. All right. There weren't any instances where we would get a 0 just from the way I was making the selection here. So I need cosine of x to be equal to 1 and sine of y to be equal to 1, or I need cosine of x to be equal to -1 and sine of y to be equal to -1. That's the only way I'm going to come out with a relative max, right? So now from all of the critical values that I have available to me, I can now start putting together, an exhaustive list, really, right? So I'm looking at cosine giving a 1 specifically. Let's just do it one at a time. Well, that's going to happen at 0, 2 pi, 4 pi, any even measure of pi. All right. So I'm looking at 0 plus 2 pi, and it's all going to be where k is the set of integers. So 2 pi k. Sine would have to be equal to 1. So that would happen when we're dealing with pi over 2 plus 2 pi k. Or the other possibility is cosine and sine are negatives, in which case I'd be looking at pi plus 2 pi k, guaranteeing a negative, and pi over 2 plus 2 pi k. All right. Now, so that's one set of conclusions. It looks like we have instances in which we'll have a relative max, which is great. That's what we went into this hoping for. So what we really ended up with if you kind of think about what we did so far, I'll say we're only a third of the way through the solution, but we've done the lion's share of the work. So the hard work's already done. It's just a matter of kind of wrapping it up. But if you really think about it, this really is the solution, or the method for finding the solution, because the alternative would be to use the second derivatives test. Now, if we did that, and we could, we would have to pretty much do everything that we're doing right now, just instead of evaluating it by subbing it into the original function, we would have to evaluate by subbing it into the discriminant, and also subbing each of the critical values, each possible pairing of critical values, each type of pairing of critical values into not only the discriminant, but the second order partial with respect to x, right? It's the same, just an extra level to it, right? Since it seems anyway, and we'll cross this one last bridge in a couple minutes, but it seems as though we're really on the lookout for a max of a 1, or a min in a min being -1. Once we find the different ways in which we can get there, then we're pretty much done with that part of the problem. Check. Shouldn't the y value be 3 pi over 2 plus 2 pi? What did I write? Pi over 2 pi. Oh, thank you. Thank you. My eye was drawn to what was immediately written above it, and I just wrote it again and said it again. So classic Bob. Anyway, so that's one possibility. Now we want to look at ways in which we can get a negative. So specifically a -1. So that's the relative min. Now we already got kind of a pathway to that. That was this computation that we did over here, where we found cosine of pi, sine of pi over 2, giving us a -1. All right, so that's going to happen when either cosine of x is equal to, because again, we're working with cosine comma sine. So cosine of x is equal to -1, and sine of y is equal to a +1, or cosine of x is equal to a +1, and sine of y is equal to a -1. Right. Now you can start stealing some of your work and repurposing it, but I gotta say, if you're anything like me, you just got to be careful when you start copy pasting stuff, because that's whenever I screw something up, that's how I screw it up. Right. So we're looking at cosine of x equals -1. I did that over here, so I could just steal this guy. Sine of y equals +1. That was over here. No need to reinvent the wheel. Or I need cosine of x equal to a +1. That's this one. Which again, I said this before, but I keep writing it this way. You could write that as 2 pi k and not have the 0 plus. All right. And sine of y is equal to -1. That's one of those where I'm glad you pointed out the mistake, because I would have just compounded it. Right. So these would be the possible values that would give us a -1. Right. So now it looks like we have the pathways to get us to relative min. But the unfortunate, I was going to say byproduct, it's really just the unfortunate consequence of all of this is that we still have to identify any saddle points right? Because saddle points still work their way into critical values. It's like, even if you're confident that you got all your relative max and min values, you still have to evaluate what's going on with the other critical values. One, to make sure that they're not sneakily another relative extremum, but also saddle points have value too, right? That has meaning also, right? So we did all of this by evaluating an X value from the first group and a Y value from the second group. So all of this for a drop of blood, not too far off. So all of this is part of this component here. Dear Lord. So now what we got to do is look at an X value from the second group and a Y from the first group. Okay. So my X values here boil down to, our possibilities. And we could do, again, we could do the what if game, and see how that plays out. But, it's still going to ultimately end up being the same kind of computation. So if there's a way that you're comfortable skipping steps, then by all means go for it. But what I'm going to do is I'm just going to carry out an approach similar to what we just did. So it's really the idea that if you look at the X values from the second set, they're the same as the Y values from the second set. Same idea for the X values and the Y values from the first set. So really, it's just it's a role reversal, right? So I can actually do all the stuff that I did over here just by swapping the X with the Y. All right, so let's see how that plays out, at least for a few computations. All right, so let me say I have, well, I did X equals, I did Y equals pi over 2. I'll do X equals pi over 2. That was the first computation. And previously I did X equals 0, so now it's Y equals 0. Right. So that would be F of pi over 2, comma 0. Into the original function, cosine of pi over 2, sine of 0. Well, that's great news so far. Result of 0. All right. So let's try that again. X is equal to 3 pi over 2. And Y is equal to pi. It actually won't take you much longer to realize, if you haven't already realized, that we don't really have much left to do here, because by switching the roles of these radian measures, we're actually taking values that previously made sines and cosines into ones and negative ones. But now, if you really think about it, if you take a value, because of the nature of co-functions, if you take a value that makes a sine function equal to 1, a radian measure, and plug that into a cosine function, that's automatically going to give you a result of 0. Right? It's just like the complementary relationship between angles, like the cosine of 30 degrees is equal to the sine of 60 degrees. Like any two angles that add up to 90 are complements, of course, but the way they work out in trig functions is that their roles reverse. So for example, sine of 30 and cosine of 60 have the same value. So sine of 0 and cosine of 90 have the same value, or in this case, 0 and pi over 2. So it kind of stands to reason that we're going to get zeros for every one of these, regardless of what pairing we come up with. So, I mean, for giggles, you could do the last one, but it's not going to make a difference. So instead of X equals pi and Y equals pi over 2, it becomes X equals pi over 2 and Y equals pi. All right, so F of pi over 2, comma pi, result cosine pi over 2, 0, sine of pi, 0, 0 times 0 is 0. Right, so it really doesn't matter how you shake it out here, you are going to come up with a 0 as a result, no matter how you slice it. Now, I mentioned before that we definitely needed to figure out a way in which we could make a determination that we are actually coming up with the relative max and min values. All right, what we have here are saddle points, right? Because they're neither the highest nor the lowest points, yet they're still critical values, right? And these happen, if you look at all of the x values that we're working with here, they're all from the set of pi over 2 plus pi k. And the y values of, well, really anything from the set of 0 plus pi k. Right? So it begs the question of, okay, well, how do we really, truly, absolutely know that the set of values that we indicated as the relative maxes are actually those? The set of values we indicated as relative mins are actually those, and the saddle point, same deal. It's because we've accounted for every possible grouping of the different types of angles from the two sets of critical values. There's nothing left. There's no other pairings that we can put together from the first group and the second group in either order, x from the first and y from the second, or x from the second, y from the first. There's no other way we can slice it out. So we've accounted for everything. And the only z values that we've come up with at any point have been -1, 0, and +1. So that's telling us if we know that the local extrema has to come or have to come from the set of critical points, and we've accounted for all the critical points, whatever the highest value is, that's your max. Whatever the lowest value is, that's your min. And whatever's not the highest nor the lowest, that's going to be your saddle point. All right. So we were able to do this one without the second derivatives test, but I can tell you that the only thing that you would be doing with the second derivatives test is verifying, after we did all this work, verifying that these points that we just came up with are in fact, based off the discriminant, going to give you local min, local max, or saddle point. But since logically we made that determination, we don't have to worry about it. Right? That's the beauty of logic. You know, if you can reason it out, and that's why I incorporated the logical notation here, keeping my ands and ors straight. Yeah, I got a little lazy and I started writing the word and instead of using the symbolic notation, but it was still there. The logic was still sound. And because of that, we were able to draw a concrete conclusion that's really inescapable. Right? So, like I said, and that's a lot to digest, because between this problem and the one that we did prior to it, it's like, this doesn't seem so bad, to what the hell? You know, so what you're going to do, like I said, for homework, practice, is take a look at number 3 on this page, save question number 4 for us to work on together. So don't do that one. I mean, you can do it if you want, but we're going to do it together as a class. And then try number 5. So 3 and 5, try those problems, and you'll see that 3 is a much easier problem than what we just did. In fact, I would dare say that it's even easier than number 1. Right? And also, I had mentioned before that I would show you an example of a saddle point that actually looks like a saddle point. And this is one of them, because if you just look at the innermost part of this graph, my Apple Pencil is struggling here. The innermost part of this graph, focusing on these points here, kind of has a saddle-like quality to it, right? So it's like if you're saddling up a horse, this is the type of surface that you might expect yourself to be sitting upon. All right. So some saddle points actually look like they're part of the saddle, and that would be at this location. My money's on 0, 0, but you'll let me know. All right. So that's where we're going to leave it for tonight. I didn't want to go too crazy because this is some heavy stuff. But next class, what we're going to do is we're going to kick into Lagrange multipliers, and then we're going to start talking about multiple integrations or multiple integrals, and then we'll start moving towards the next unit test in preparation. I hope to have by the end of the day tomorrow the practice test revised and set up for you to look at on Blackboard. It's going a lot slower than I thought. So just give me the end of the day tomorrow. If you don't see it by then honestly, it's probably because I forgot to post it. So that if that's something you're interested in getting cracking on, wait till the end of the day tomorrow, then send me a message. All right. So I'm going to stop the recording. I'm going to stop the share.